Good morning and good afternoon. My name is Professor Duke Orata. We are continuing with our thermodynamic lectures. Today I want to look at steady-state flow process. Steady-state flow process and develop the first law of thermodynamics for steady-state flow process. For steady-state flow. Now, what is a steady-state flow? A steady-state flow is a flow whereby the conditions within the apparatus, for example, when a fluid is flowing through an apparatus, the conditions at all points in that apparatus are constant. For example, the mass flow rate will be constant throughout the system, the volumetric flow rate will be constant throughout the system, and there is no accumulation of material or energy within that system. So a steady state flow is case where conditions, the fluid, at all points is constant. One of them, for example, you can talk of mass flow rate, no accumulation of material or energy in the system. Very important for us to note that. So when you develop the first law of thermodynamics, we say that du was equals to dq plus dw. That was for a non-flow process. For a non-flow process, du is equals to dq plus dw. But now, because we are dealing with a fluid and the fluid is flowing, it has kinetic energy. If it is raised above a certain reference level, what we call the datum level, then it has a potential energy. So we have not only now to deal with the internal energy, but we have to deal with the kinetic and potential energies. For steady state flow, we now factor in kinetic energy and potential energy. And let us have a schematic which will show us how this happens. So we have our unit. Our unit. So let's call this portion section A. Let's call this portion section B. And let us say this is our heat exchanger. In other words, it can allow heat to be transferred to the surroundings or from surroundings into the system. Let's call this the work machine. Let's call it a turbine. And doing some form of work which you can call shaft work. And let us say that the datum level, point of reference, that we call datum level, is the one we have marked there. And so the height of this section, the datum level, let's call it HA. And for section B, that height HB. And of course, this is the difference between the two. Delta H will be equal to HB minus HA. And if we consider only a unit volume, unit mass, cylindrical, say cylindrical, that unit mass, one which will be flowing through our system. And we are saying when it is here, that unit mass, there are forces acting on it, and it's acting on forces. So that basically, it is not doing work, because it is being acted on and it is acting. So we assume those two forces cancel out. Now, if we assume that the thermodynamic functions at section A can be categorized as the thermodynamic functions at section A as the volume of the cylindrical unit mass, that's the specific volume of the cylindrical mass, and its internal energy, which is capital UA is its internal energy. Its velocity we can call U small u, that is lowercase u, velocity. And what else do you mean? Its length, L, will be its volume divided by area, where A is its cross-sectional area. Similarly, for section B, the thermodynamic functions again will just have the subscript B instead of subscript A. We'll have VB for specific volume. We'll have UB for internal energy. We'll have U small b for velocity. Now, let us work with our system. So, we have said that this unit mass or the fluid is flowing through this particular system, and the conditions at all points in this apparatus will be constant because it's steady state flow. And we said volume, I talked of volumetric flow rate and I talked of mass flow rate. It's very important to know what those are. The volumetric flow rate is very simple. Let's call it R, and this is important. It's an important element in what we call continuity equations, which are based on Bernoulli principle. The volumetric flow rate is cross-sectional area times the velocity. What is that? Cross-sectional area is length squared, velocity is length over time, and clearly you see length cubed over time. That will volume over time. Anytime you see the word rate, means time is there. Similarly, mass flow rate will be given by mass flow rate, that is rho AV, where rho is density, A is area, V is velocity. Very important to remember those equations. Again, the dimensional analysis, density is mass over volume, area is length squared, velocity is length over time. So length squared times L is volume, cancels that, you are left with mass over time, and that is mass flow rate. So those are constant in that particular system. Now, let us now work with our system. I hope you have this picture, this scheme in your life. Section A, elevation above the datum level is HA. We have a heat exchanger, so we can exchange heat between the system and the surroundings. You can exchange heat between the system and surroundings. Let's just call that Q. And of course, you have the turbine where work will be done. If you look at our earlier lectures on turbines, you can look at the Pelton turbine where we have the blades and you see the nozzles and what they do and how we achieve that work. But what we have is shaft work, which can be rotating or reciprocating. Again, I encourage you look at our earlier lectures in internal combustion engines and so forth, and to do with the turbines, and you will see what we're talking about in terms of rotating and reciprocating units. And that's important for us if you want to delve further into how this system will do work. But basically, the work is transmitted from the system through the turbine processes. Now, let us now put down our first law equation. So our first law of thermodynamics now for steady state flow, we now have internal energy, du, plus the kinetic energy plus the potential energy. And that is equals to dq minus dw. Like I said, you can have plus or minus there. That is a notation. Whether if you choose that your system, when it has done work, is negative W, or if it's positive W, that's your choice. The key thing is you use it consistently in the system. So you can use plus or minus depending on your notation. So this is internal energy. This is kinetic energy. This is potential energy. So in the non-flow process, basically what you are saying is that we are assuming kinetic energy is 0 and potential energy is 0. So we are left with the first law, du is equals to dq plus or minus dw. But now, because those are important, the fluid is flowing, kinetic energy is important, and you have potential energy, so we have to take into account that. Now, let's calculate work at section A and kinetic energy and potential energy at section A and at sections B. So work at section A. Remember, work is pressure times volume. And remember what is pressure? Force over area. Volume is length cubed. So force over area. Volume divided by area will leave you with the length. That's how you get even the length of that cylindrical unit. Just take its volume divided by its cross-sectional area. And so what we have here, remember, that is force over area. And volume is area times displacement. So the area cancels. We have force with length is work. So that PV is always work. So the work done, section A is PVA. Work done at section B. Work done at section B, let's just call it section A and B. Section B, WB, will be PBVB. So the total work is, we have the shaft work minus PBVB minus PAVA. This is our total work for our system. The kinetic energy, which I'm calling KE, kinetic energy, will be given by velocity at the exit, UB squared minus UA squared over 2. So that will be delta U over 2. So delta U squared over 2. That's velocity squared at exit B and velocity squared at entrance A. And similarly, potential energy, which I'm calling PE, will be given by G into the elevation at B minus elevation at A. That will be G delta H. And because now we are talking about deltas, not the infinitesimal quantities, just remember that identity I told you. If you integrate the internal energy, it will be delta U. It will be U, that is 1, 2, will be U2 minus U1, and that will be delta U. But when you integrate dq or you integrate dw, these are not path functions. So it will just be q and that will be w. These are path functions. So it will just be q and w. This is a state function. And please go through our lectures on state and path functions. These are path functions. So in other words, we will now get, for this system here, we will now get, when we marry them, when you marry those two quantities, we now get delta U plus delta U squared over 2 plus G delta H is equals to Q minus W here, which is W shaft minus delta PV. Remember, That is PB minus PV VB, and that becomes delta PV. And so if we rearrange these quantities, we now have delta U, let's change internal energy, plus delta PV plus the kinetic energy plus G delta H is equals to Q minus W shaft. And so we are getting there. We are getting there. We're in good shape. So we are moving on very well. We are getting there. So you realize that H is equals to U plus PV. It's a very important thermodynamic relationship. And remember, don't plug in nRT unless you're dealing with an ideal system. That's a fluid which has a characteristic equation or equation of state. PV is equals to nRT. Otherwise, it's just pressure and volume of the system. So that this quantity here can now be called delta H. So that what we have now is delta H plus delta U squared over 2 plus G delta H is equals to Q minus W shaft. If the system was not doing any shaft work, then we can assume that is 0 if delta H plus delta U squared plus G delta H is equals to Q W shaft. So let's remove the categorization shaft and just leave it as work. Now, this is the first law of thermodynamics for a steady state. Flow system. Now, notice we now have the kinetic energy, we have the enthalpy. This is enthalpy change. You have the kinetic energy change, potential energy change equals to Q minus W. For the non-flow process, it was simply delta U is equals to Q minus W. So if we assume that kinetic energy is negligible, potential energy negligible, then we will have, if we assume they are negligible, which is an assumption which you can use significantly, then in that case it will simply be delta H is equals to Q minus W. And at that particular point, I think we can now stop. We'll pick up with our lectures later.